For this lesson objective, we're going to learn about barometers, manometers, and learn the swim-through technique, which will help us to solve manometer problems. I'll start off by introducing you to what's called a mercury barometer. It's a relatively simple device that's used to measure atmospheric pressure relative to zero absolute pressure. You know, when we solve problems, we're given the atmospheric or the surrounding pressure, but it has to be measured somehow, and it's measured using what's called a barometer. And the barometer uses the weight of the mercury in the tube, and it causes that fluid level in the tube to drop. However, the fluid in the basin and the atmospheric pressure acting on the fluid in the basin reaches some state of equilibrium with the fluid that's trying to flow down the tube, at which point it stops and the pressure can be measured. To solve for atmospheric pressure at state 2, though, we have to make a couple of assumptions up front. We have to assume, of course, that the fluid is static. We also have to assume that the fluid is incompressible, and we have to assume that the volume at the top of the tube, the pressure is so small that we can assume it to be a vacuum and that pressure is 0. Now, in order to solve this problem, we use equation 2.13, which was introduced in a previous learning objective. And it states that the pressure at position 2 is equal to the pressure at position 1 minus the density times the acceleration due to gravity times the difference in the height, which we annotate as z. Now, putting in my values for my barometer, knowing that pressure 1 is a vacuum, so the pressure is 0, and calling Z2 my reference datum, or 0, I can then state that the atmospheric pressure, or P2, is equal to the density of the mercury times the acceleration due to gravity times the height difference in the fluid. Now, we can apply that same principle to what's called a manometer. And a manometer is slightly more complex than a barometer and has a different purpose, but very much the same. And the solution to solve it's very similar. A manometer is used to measure pressure using fluid in a column and measuring that column height in order to do so. Again, the same assumptions are made that it's static and incompressible fluid. However, as you note in figure 2.4, there are multiple fluids and multiple variations of height. So I can't simply reuse equation 2.13. I simply have to use a variant thereof that includes all the different densities and all the different heights. And in your book, that's given as equation 2.15 alpha. And what it states is that my end pressure is equal to my starting pressure plus the summation of all of the densities and all of the differences in height times acceleration due to gravity summed together. And recalling that my specific weight is equal to my density times gravity, I can also rewrite this equation as my end pressure is my starting pressure plus the summation of all of the specific weights of the fluids times their changes in height. And that's given in your book as equation 2.15 Bravo. We use this equation in what's called the swim-through technique. And we use the swim-through technique to solve for manometer. And the swim-through technique is figure 2.5 on pages 2-7 in your textbook for your reference. The first step is to identify all the fluids and label their interface. And in this figure on the left-hand side of your screen, that's already been done. So we know it's clearly delineated the differences between the fluids, their heights, and we've identified each individual reference point that we want to use in our equation. The next step is to start at an end or at a known pressure. And in this case, I know at state 1, my pressure is atmospheric. So that's where I'm going to start. So I'm going to drop my little diver there, and that's where we're going to begin. Then my next step is to add or subtract pressure changes based upon whether I'm swimming down through the fluid or swimming up through the fluid. And it makes a lot of sense if you just put some realistic experience to that. If I swim down, I have to add the hydrostatic pressure because as I descend, the pressure is going to increase. If I'm swimming up in the manometer, the pressure is going to decrease, so I subtract that hydrostatic pressure in my summation equation. And I'm going to repeat this process until the final point is reached. And so I'll take my little diver, I'm going to swim through the first liquid. And I'm going to measure the change in height in that liquid based on the difference between where he started on my z-axis and where he ended on my z-axis. And I'm going to continue until I reach my end state, at which point I can solve for that pressure at the end state. Again, during that, for this example, swimming through that gas, my height is based upon where I started in that gas to where I ended up and determining whether I had to swim up or down to reach that different point. I then substitute all the values and I solve for my ending pressure. Now, this is easiest seen by doing an example problem. So we're going to work through example problem 2.2, which is on page 2-7 of your textbook. And problem 2.2 states that a manometer contains several fluids, as shown below. And we need to determine the absolute pressure in kilopascals of the water in the bulb at state 5. So let's use our problem-solving steps. The first is to list the known, and in this case, we know that the manometer contains several fluids, and that can be intimidating, but don't be afraid. If we do this swim-through technique, you'll find it's relatively easy, and it's very organized. It's going to take you through that process, so don't be intimidated. Next, we have to list our find, and it asks us to find the absolute pressure, note the units in kilopascal, of the water in the bulb at state 5, and then our diagram and data is shown at the right, and that diagram and data contains all of our different fluid heights already marked. It contains my starting pressure at atmospheric, and it also lists my specific weights and or specific gravities of each of the fluids, and each of those different fluids are clearly marked so that we can measure those heights. This is all important information that you need to have on your diagram and data when you draw it up for your work. Now we have to make some assumptions before we can continue, and we're going to use the same assumption we used on the previous slide, is that all the fluids are incompressible. Now in order to do our analysis, we're going to apply the swim-through technique. And for P-start, we're going to select the atmospheric pressure at state 1 because that's what we know. And we're going to select equation 2.15b, which is in terms of specific weight, because the specific weight is the prevalent property that was provided to us, with the exception of oil, which is specific gravity. And I'll show you how to attack that here in a minute. So to continue our analysis, I've listed equation 2.15b at the top. And let's work our way through it with our little diver. So my pressure in my water at state 5 is equal to my atmospheric pressure, where I'm starting. And he's going to swim down from 1 to 2. From 1 to 2, he swam through oil. So I have to add the height change in the oil times the specific weight of the oil. Now again, the specific weight was not given. We were given specific gravity, and I'm going to show you how to solve for that. But let's continue with the swim-through technique, and then we'll go and attack that problem. Now I'm going to swim through the mercury. And as I swim through the mercury, see, I initially go down, then I come back up again, and I go up and down the same amount, so that cancels out. So I'm only concerned about the height difference in the mercury. And you can see that my swimmer had to swim up, so he was ascending, so he was swimming up through the fluid, so I have to subtract that because the pressure is going to go down as he swims up. And again, I'm adding the specific weight of the mercury times the height difference of that mercury. And I'm going to repeat this process for the remainder of the fluids. In air, I swam up. My overall change was up 30 centimeters, so of course I'm going to subtract that. And then I'm going to swim through the water down to the centroid of the bulb, and that's going to be my difference. Now because my diver had to swim down, and therefore the pressure was increasing as he swam through the water, I'm going to add the specific weight times the height difference. Now let's compute the specific weight from the specific gravity for the oil before we put our numbers in and solve the problem. Now recall that our specific gravity is equal to specific weight divided by the specific weight of water at 4 degrees Celsius. Now the specific weight of water at 4 degrees Celsius, that's a known quantity. It's 9,810 newtons per meter cubed. And the specific gravity was provided in the problem as 0.85. And again, that's unitless because it's a ratio. So I can use that and solve for my specific weight of my oil. My specific weight of my oil, therefore, is 8,338.5 newtons per meter cubed. Now let's go back to our equation that we wrote up under our analysis in the beginning. And we're going to substitute values, and then we're going to solve. And it's that easy. So my pressure at my water at state 5 is my starting pressure of 101.3 kilopascals plus the summation of all the specific weights and their heights. I note that I carried those negative signs through appropriately. And I also want you to note at the end of the equation that I had to divide the values that are in the summation by 1,000. The reason for that is the answer has to be in kilopascals, and my atmospheric pressure was already given in kilopascals. But let's just look at the first fluid, the oil. And you see that it's 8,338.5 newtons per meter cubed. And I'm going to multiply that by the height, and notice that I changed the height to meters from centimeters to 0.4 meters. The meters cancel out, and that gives me newtons per meter squared, which is only a pascal. And the same is true for each one of those fluids. So I have to divide by 1,000 to get those into kilopascals, so I can then add them to my atmospheric pressure and get my total pressure in the water, at state 5. And the answer we come up with is 89.09 kilopascals. Double underline answer, you got it. So it's that easy. Regardless of how many fluids you have, you follow the same process and you can solve the problem. Now, in your ME350 reference data card, your manometer swim-through technique is listed under static fluids. And an MC311 reference card, it's also listed under static fluids.